Here's a summary of everything that we've done with Laplace Transform as of yesterday. We talked about their transform definition, going from our real world, our T world, into the S world. We talked about some basic transformations from the T to the S, and then you're going to be required to do some algebra in the S world, and then after you do your algebra, your solution is going to be based on being able to take you back to the T world. And since we are dealing with differential equations, I guess it would be important to know how to transfer a derivative of a function from the T world into the S world. So I think with that, we're ready to do some actual differential equations using Laplace transforms. I guess first we should try to simplify this complicated formula, and I wrote it down last time, but let's try to remember what our possible transformations of derivatives might look like. So if we just have the first derivative, y prime, the Laplace transform of y prime would be prime is n is equal to 1. We have s to the first power times capital Y of s, which is the function that we're looking for in the S world, minus you take s and you subtract 1 from n. In this case, n is equal to 1. And we get 1, and so you just have y. Oops, yeah, y of 0. Sorry. So it's information about your initial conditions, and for easiness sake, we'll just have our starting point at 0. We'll have our initial conditions start from 0. And we should be able to generalize this. Well, I mean, the generalized formula is here, so we should be able to just easily compute the other stuff. So second derivative is s squared y of s in the function in the y world minus s to the first power, n is equal to 2, times f, or the original function, evaluated at 0. And then you run down the line, you get one more, which is s to the 0 power times y prime at 0. In the book, they talk about boundary conditions, but we're not going to go into boundary conditions in our class. Let's just focus on initial conditions. And for single variable, there's only one initial condition. For not single variable, but for the first order, there's one initial condition. For second orders, we have two initial conditions. So we'll just go with these. All right? So let's do an example of a differential equation. One, in fact, that we might even know of. Number 32 is one that I think I know. Wait. Yeah, well, yeah. Number 2 is going to be an exponential. I think number 31 is also exponential. Maybe not. I don't know. In any case, we should be able to solve these differential equations. This is for first order linear, so we can we can solve this using series. That's if we want to go the long way. But we can solve these using, what's that first thing we learned in the Chapter 2? First order linear. What? Integrating factor. So if we find an integrating factor and multiply it out and stuff, we should be able to solve for this. Should we do that, or let's just go into Laplace? Let's just go into Laplace transforms. All right, 31 or 32. Let's do one. Which one? 32. Let's do 32. All right, so we have a 2 sitting outside, and then we have a dy dx. Let's just call that y prime. I'm just rewriting it, it looks like. Now this is where I'm going to go into the S world, right? So because it's the transformation is a linear transformation, we can break this up to the different sums, and then we can even take the constants out. So we have, let's say we're not quite there in the S world yet. This is our S world color, orange. No, this is our transition color. So we have 2. We want to take the Laplace transform of y prime plus the Laplace transform of y is equal to 0. Now, to get into the S world, we do this Laplace transform. And the Laplace transform for y prime, we just did that. That's S capital Y of S minus y of 0. Is that correct? This notation. So when I think we used F in our last example, or in our example last time. So this L bracket something means we're going to take this into the S world. We have, we talked about it, and we might have done 1 or 2 things, but we didn't really. This is our first time when we're actually doing the differential equation. So, so that's that part. This part is just there's no derivatives involved, so we're just looking at transforming the y into capital Y. And then we have 0 on the other side. Okay? All right, so that's all we got. Now it's algebra time. We're in the S world, and we're going to solve for differential equations using algebra. So let's see, we have 2s capital Y minus 2 times y of 0 is negative 3. So let's drop that information. From the initial condition. Plus y of s equals 0. It looks like I want to collect all the y's. So I have a 2s plus 1 y of s on one side, and to have a negative 2 times negative 3, which is positive 6, brought over to the other side would be negative 6. What? Oh, this is, I don't know how I can write my s, because I got mixed up last time too. I wrote 2s and I thought it was 25 and threw me off. How should I write my s? Should I write my s different? At the end, or like that, or just at the tip? Right here? Okay. So that would be an s versus a 5. And then if we solve for y, we get negative 6 over 2s plus 1. Now, that looks great. That was easy algebra. And if I had a nice machine that would take any function that I get in the S world and transform it back, that would be great. But I don't have a machine. What I have is a list of functions in S that I would have in the S world that I need to use somehow to transport it back. Okay? Now, looking at my list, or looking at my solution here in S, this is my solution, I need to make this look like one of these things. Probably the exponential function. So let's take a quick snapshot of that. Can I undo? So let's take a quick shot of the exponential function. So this is our key. We hope to be able to rewrite this thing to make it look like that somehow. If I can factor out a 2 from the bottom, that would be great, right? So this should actually be the transitional period here. Well, I'll kind of just cover it in that. So we have y of s is equal to, the minus 6 is a constant. Let's move that out. And let's pretend that we factored out a 2 from the bottom. Now, we can't just take a 2 out, right, and then have it all fine and dandy. So we need to force a 2 out of this 1. So that becomes what? 1/2. So now it looks like this. Well, except it's plus. We'll just say minus minus, right? Or if you want, minus 3 times 1 over s minus negative 1/2. Now it looks exactly like that. You have a constant negative 3, but because this is a linear transformation, those constants can just move outside. We just focus on this thing. Good? Now we inverse L. We take it back to the real world. I guess I should have took that negative 3 out, but I'll just leave it there. And then our real world answer would be little y. Now we're in t again. And this is going to be a negative 3 constant. And then this 1 over s minus a is going to be e to the negative at. So this is e, not negative, but e to the negative 1/2 t. Okay? Now, if we would have taken this problem and did that integrating factor business or whatever else we might have been able to do to solve for this, we should get exactly this for this IVP. It's an actual initial value problem. That was a good start. That was a good first problem. Usually you do a first problem and get stuck at some horrendous looking algebra stuff. All right, this is a good one. Okay, we good? Orange stuff would be my transition from one world to the other. So I'm in T here, and when I start my problem in T, and then I transition to my S world, and then now I got my answer in S, and then now I transition back into the T. Yeah. Kind of like that graphic that I showed you guys, right, yesterday. You go in T, you dip down to the S, and then we go back to the T. It's like another world. So let's, well, I suppose we could do one of these other ones, but let's jump into a second order already. Here's a bunch of second order differential equations here. Should we do one? Which one should we do? 37 has a sign. You interested? Okay, let's do one with a sign. See how far we get with this business. Okay, I won't rewrite everything. Let's just go straight into the translation phase. So we need the L of these things. Oops, there's no prime in that one. So the square root of 2 is a constant. We can leave that out. We have sine root 2 times t. So in the S world, our second derivative is going to look like, do you remember? You remember? It's like S or S squared. I think it's S squared. Minus S times, now is this y of 0 or y prime of 0? Y of 0 minus, and then S to the 0 power, which is 1, times y prime of 0. And then there's a plus in between. It's linear, so we can do it one by one, piece by piece. And linear transformation, or the Laplace transformation of y is just capital Y. We good with that? Ask a question. These ones? They came from, according to our theorem for taking derivatives, if you have f, the nth derivative of f, like the second, let's say when n is equal to 2, that's like the second derivative, then this would be s squared times the function in s minus, this is s to the 2 minus 1, which is s to the first power, times this, and then the next term would be s to the 0th power times this. So these, whenever you do Laplace transform, you're doing them from an initial value problem, and so your initial conditions are going to be involved there. So your initial conditions for your second derivative look like this, or they're incorporated into that Laplace transform.
So it's not s y prime of 0 and then minus, it's not absolute.
No, according to this, it's just the highest power of s is multiplied with just the y in s, and then the next highest going down starts with the original function, and then the function, the derivative starts climbing after that. And then your last term is going to be your whatever the highest derivative is. So in the case of the second order differential equation, our highest order derivative from the initial condition is the first derivative. So if we had a third order differential equation, then we would have up to y double prime here. All right, so we got those two things figured out, and the right-hand side now will be a sine function, and I don't know, this is something that you probably should memorize if you do this a lot, but if you don't do it a lot, I guess it's fair enough to just have a handful of these things written down somewhere. The sine function is a constant times or divided by s squared minus the or plus the constant squared. So constant divided by s squared plus the constant squared. So the square root of 2 is sitting out here. That square root of 2 is irrelevant of this square root of 2, or independent of. So the constant k is square root of 2 divided by s squared plus the square root of 2 squared. Yes?
Why can't you just like take out the code?
Because this square root of 2 is inside of the sine function, and this square root of 2 is that constant that can go outside. So those are two different. It's unfortunate that they're both square root of 2. It would have been better if they were different, but they are two different constants in this context. All right, got some simplifying to do here. Algebra, all algebra. So I'm going to underline my y of s terms. So I have an s squared plus 1 y of s minus, I have an s here times y of 0. Y of 0 is 10. And y prime of 0 is 0. So remember, those are from the real world. And then on the other side, we can simplify this a little bit also. This would be positive 2, just the 2, over s squared plus square root of 2 squared is 2. All right, so I think we need to bring all the s's over to the other side first, or at least this 10s over to the other side, and then divide. So we got s squared plus 1 y of s is equal to 2 s squared plus 2. Negative 10s becomes a positive 10s. We probably should, what should we do? We probably should combine these two fractions, right, into one fraction. So, common denominator. S squared plus 2, S squared plus 2. This will give us, I have a 2 and then a 10s, so let's see, 10s cubed plus, this is an s, plus 20s plus 2 all over s squared plus 2. So my y of s, finally got it by itself, is 10s cubed plus 20s plus 2 divided by s squared plus 1 s squared plus 2. No, I think that came from the square root of s squared. Is that right? So I think that's correct. Yeah, I think it's good. Nothing. Up here? Well, what do you mean? Y prime of 0? Oh, not s of 10, but s times 10. So this is s times y of 0, and this is times 10. Is it okay so far? Okay, all algebra. Now, now comes the fun part. We want to be able to break this up. And if you're looking at this, you know, the problems that they give you in Calc 2 when you have to do partial fractions is they give you usually nice, easy functions, or they tell you how to decompose it, but they don't ask you to follow through with the work. But this is something that needs to be decomposed. And when you're looking at this, what you need to realize is that the denominator has two factors that are irreducible quadratics. You can't reduce them, right? S squared plus 1, S squared plus 2, you can't factor that out. So they're irreducible quadratics. And furthermore, the power in the bottom, the degree of the polynomial on the bottom is 4, the degree on top is 3, so you can't really simplify that anymore. The only good thing we got going for us is that the denominator is already factored. So from here, you need to do partial fractions. And with two irreducible quadratics, what you can do is you can break this up into the first quadratic plus the second quadratic as your denominators. And then you set up your numerator so that the numerator doesn't have a or b, it's not constant, but it's actually a linear. You have to go 1 degree lower than your denominator. So what is your numerator going to look like for the first one? So we're using s as our variable plus b. So as plus b, and you have to solve for a and b. And then you have c s plus d, and then you solve for c and d. Okay? So as fun as this could be, I'm not going to do it that way. I'm just going to use Mathematica to help me find it. So there's a command in Mathematica where I can take 10 s squared, let's use that notation, cubed, plus 20s plus 2, and let's divide this by the factor s squared, squared plus 1 squared plus 2. So if you take it apart, it looks like your A should equal to, what is it, 10 should equal to 10, and your B should equal to 2, and your C would equal to 0, and then your D would equal to negative 2. Well, S is just a variable. It's not equal to anything right now. That just tells us that we're in the S world. So, given our decomposition, I guess it's called the partial fraction decomposition, we have a solution for our y now. Oh, I should have mentioned while we were here and this is looking at this big fraction over here, this big fraction is not anything that looks like one of the things that we can take back, right? So by doing a partial fraction decomposition now, we might have a chance to make it look like one of those things. And what I'm going to do is I'm going to break this up so that I have s squared plus 1 and s squared plus 2 as a denominator, with the numerator just being one term. So that means I'm going to break up this s squared plus 1 into 2 times 5 is 10, so that's 10s over s squared plus 1. And then 2 times 1 is 2, s squared plus 1. And then the last term, I get negative 2, s squared plus 2. Okay? So these look simpler, and they will, in fact, be one of these guys, sines and cosines. So if you could try to remember, the sine is has a transformation. The sine has a transformation that has a constant on top. The cosine has a transformation that has the s variable on top. Okay. So that will bring us to our solution in the real world, little y of t. All right, 10 is a constant. Let's move that 10 out here. S over s squared plus 1. K is equal to 1 in that case, and the s, the variable, is on top. And so that would be s. And that's a cosine. So this is cosine 1, or I guess we should be really looking at the square root of 1 times t. That's the first one. The second one, we have a constant 2 sitting up on top. And we have, that would leave us with 1 on the numerator, 1 over s squared plus 1, that's the sine t. I guess the next one is a negative. Now, this one. I'd like to take the 2 out. But if this is going to come back as a sine function, I have a k squared in the bottom. So this might need a little bit more attention here. So the negative 2 is a constant that can come out. We got s squared plus 2. But I want to write that so that it's something squared. So what is 2 as something squared? Square root of 2. Right? Now look at this trick. That's not a trick. I want this to have a matching k on top. So if I just multiply the top and the bottom by k, then I would match. So guess what? Whoa, what happened? That's my constant out there. So 2 over root 2. I guess I should be in blue. 2 over root 2 times, now this whole thing can transform into the sine function. And not just the sine function, it's a sine with a coefficient square root of 2, t. Yeah?
So in the second one, when we did, so 1 and 2, they don't match.
Yeah, but the 2 is a constant that would be taken out anyways.
But when in the general term it says sine kt equals, so why didn't write k sine equals? Or a constant, like?
Because this isn't equal to this is a transformation. This is a transformation to take us back to t. And it's not like we're taking the derivative or anything. What we did here, or if we were to do this again, what we did, well, we didn't do it. But if we were to look at the proof of this, we would run through the this transformation to go from sine kt to this thing. And so this is just our vehicle. This L transformation is our vehicle to go from the t world to the s world. And then when we want to go back from the s world to the t world, we have to match it exactly as how we got it there. And we have to match the functions exactly the way they're written. So the k that's sitting up on top here, it's not really as important as the k down here. And if there was a k down here, then you want to adjust your constant up on top. Now, the second one, I kind of just waved my hand because we were lucky enough to have this to be a 1. Because this is a 1, then there's a known 1 over here that we didn't need to worry about. But if this was a 5, then that 2 that I took out would be a 2 that I would take out, but then I have to worry about what this number is in the numerator. And that's when you do the multiply top and bottom business. All right, so we got our solution. And I don't want to go through the whole thing, but if we just kind of guess at our solution, this thing, y double prime plus y, has auxiliary equation m squared plus 1 in your head. M squared plus 1 has I for the roots, plus and minus I. So that gives you your sine and cosine of just t. And then now if you look at the right-hand side for the non-homogeneous equation, your variation of parameters tells you that you're going to have, or your, what's the other one? Undetermined coefficients. Your undetermined coefficient tells you that you're going to have a function that would have a sine squared of 2 times t as your particular solution. Now, normally this would get matched up with a cosine squared of 2 times t, but we didn't. Just happened that we didn't get that, so that's fine. So that's more or less what we should expect. And provided we did everything correctly, this is the correct answer. Whether we do it using Laplace transforms or, hell, we can do the series stuff, and we should get the alternating, the sine and cosine business there too. No, we wouldn't want to do the series stuff for this one. All right, we good? That's kind of fun, huh? No. It's not. Let's do another one. Let's do number 22. Let's see if we can try to get tripped up here. And the tripping that we're going to do is going to lead us to some more stuff that we're going to need to learn. 22. Seems harmless. All right, wait. Did we do this? Do we have a linear transformation for this? We had one for, yeah, that looks like it's going to be hard. Do we have a linear transformation for that? T to the something and e to the something, but we don't have one where it's t times e. Ah, bummer. Let's not do that one then. Let's do the first one. All right, the first one doesn't look too bad. Let's go directly into the S world. We have y prime. So that is S times y of S minus little y of 0. We have 4y, so let's call that 4y of s transformed. E to the negative 4, so let's call that, what is it? 1 over s minus negative 4. You guys got that? Okay. So let's do some simple algebra. By the way, y of 0 is equal to 2. So let's take the s plus 4 out of the y of s's, and let's bring that negative 2 over to the other side. I suppose we should find common denominators. So we have 1 plus 2s plus 2 times 4 is 8, and then that 1 that was added, let's call that a 9. S plus 4. So let's divide both sides by s plus 4. We get 2s plus 9 over s plus 4 squared. Okay, s plus 4 squared is already factored, right? And so, and it's by itself, so we can't, I mean, we can, I suppose we can split this up into 2s over s plus 4 squared plus 9 over s plus 4 squared. I don't know if that's helpful. So, does this look like any of our transformations? I don't think so. Let's see, let's take a look at our transformations again. I should just have a transformation list that would pop up, huh? Let's see, our transformation list. We don't have anything that's being squared or anything like that, right? So we're kind of stuck. And where are we stuck at? We're stuck at, instead of an s, we have an s minus something or s plus something. We're stuck at this thing. We have an s plus 4 that's kind of a little bit of a problem. So, I'm sorry you guys are taking notes, huh? So what I wanted to do is pause here and go back to my notes and talk about a translation in the s-axis. So if you're in the s world and you got s plus 4, s minus 5, s minus 1, stuff like that that's happening, turns out that we can use some information about a translation that would help us bring everything back. So this is called a translation in the s-axis. Let's see if we can understand this. If L of f is equal to f, L of little f of t, the Laplace transform of f is equal to capital F, and a is any real number, then the transformation of e to the at times f is equal to f of s minus a. So multiplying by e to the at in the real world, in the t world, is equivalent to a translation in the s world. So if we have a translation in the s world that's happening, that's equivalent to multiplying by e to the whatever translation is times t in the t world. So that means if this is your relationship for your linear transformation, then your inverse transformation is going to be this thing. What does that mean for us? What does that mean for us? So let's let me take a quick picture of this. And bring it back to the current page that we're working on. So this is our translation that's going to help us bring everything back to the t world. And let's go back to the s world and see what we were working on. We were working on y of s is equal to 2s plus 9 divided by s plus 4 squared. Now, it's the s plus 4 that we got stuck on, right? The numerator is just going to be the numerator, and we're not going to be able to do much about the numerator. But the s plus 4 in the denominator is what got us a little stuck. And so if we take this s plus 4 and imagine there was a shift of s plus 4, then we can take advantage of our theorem with the s translation. What that means though is that we want all the s's to look like s plus 4. Now the denominator clearly is s plus 4. The numerator is not s plus 4. So how can we make this numerator look like an s plus 4? Do you see my problem? I want my numerator, I want everything to look like an s plus 4 so I can do the shift. Well, I don't multiply everything by s plus 4. If you replace the s, the thing is that the denominator isn't going to get replaced because it's already there. That's how we want it to look like already. It's a numerator that we want in the form of s plus 4. So this is like completing the square, except you're not quite completing. There's no square here. If you replace s with s plus 4, but then I need this to work out to be 2s plus 9 in the end. So I have a 9. I added an 8, really. So I need to subtract an 8, really. So I added, so you add and subtract things, right? I added a 2 times 4. I added an 8. So I need to subtract an 8 to not change it. I don't want to change my problem. So is this okay? So now I have 2 times s plus 4 over s plus 4 squared plus 1. So instead of just saying plus 1, I'm going to say plus 1 over s plus 4 squared. Is that good? Now I need to go back to y, right? In doing so, I'm going to need to think about how this transformation works. So this transformation, if I replace s with s plus 4, or backwards, if I replace s plus 4 with s, I really have 2s over s. Well, I could, let me simplify this a little bit, because the numerator, or this first one, just becomes 2 over s plus 4, right? And this one is 1 over s plus 4 squared. All right, now let's do this. Well, the first one, we didn't really need this theorem, because this looks like it's just no. The sine has an s squared. Sine and cosine both have s squareds. Which one is it? Exponential. Right? S plus 4. So that is going to transform back into, wait, let me, all right, so the first one is just the exponential right here. So that one's easy. So your y of t in the real world is a constant 2 times e to the a, what's a? Negative 4t. Now the second term is a little bit tricky, and this is where the translation happens. For the second term, you have to imagine that this kind of looks like 1 over s squared if you imagine this translation from s to s plus 4, or vice versa. And so according to this, 1 over s the inverse transformation of 1 over s is what? Or 1 over s squared is what? T to the 2? T to the first power, just t. Okay? Right? Because the cosine and the sine is s squared plus something. This is s plus something squared, so that's it's different. So this is t, right? This transformation is t. So this would have transformed to t, but since there's a shift, 1 over s plus 4 shift, and that's a shift of a is equal to negative 4, your transformation happens. It's still the f function here, the t, but then you need that shift in the s is equivalent to multiplying by e to whatever the shift was in the t world. So this is going to be e to the negative 4t times t. Whoa. Some crazy stuff, huh? Oh yeah, I mean this is all second order stuff. This is a spring and circuits and all kinds of stuff. We didn't do circuits or the mixing too. We did springs, and so we're going to talk about doing spring problems using Laplace Transform. Really, this is all algebra. Kind of. It's like completing the square algebra. It's like making your S look like something, S plus 1, S minus 4, or whatever. It's just algebra. Okay? I mean, the theory behind it is definitely calculus. The transformation requires integrals, and we're dealing with derivatives and things like that. But in the S world, it's algebra, and it's algebra that you can rewrite so that you can use those transformation rules back. Okay? Yeah. Well, it's an n factorial. It's really, yeah, well, it's just 1 in this case. N is equal to 1. But if you take this, it's that transformation. And when you do that linear transformation, or not the linear, but when you do that Laplace transformation formula here, when you have your f is t to the 5th power, you're going to use integration by parts 5 times, 4 times, 5 times. And each time you use integration by parts, you accumulate that 5, and then times 4, and then times 3, and then times 2. So you accumulate that factorial. I didn't prove it. We could if we want to waste time. But yeah, that's how you would have proven that. And actually, to throw this in, one of my favorite functions. You guys should have a favorite function by the time you get out of college. What's your favorite function? No, function. It's a function. What's your favorite function? That's an equation. Function. You guys should have favorite constants, favorite functions, favorite equations, favorite theorems, stuff like that. But in terms of a function, you guys should, some people's favorite function is e to the x because they think it's cool, or sine. Okay, my favorite function is the gamma function. Okay, I you too? Oh, good. I talked a little bit about the gamma function as an aside, but do you remember what I said about the gamma function for those people that were paying attention?
That's the reason that something else works because of that.
So what's the gamma function related to? No? It's related to the factorial.
Yeah, the 0 factorial can't work without it.
The gamma function wouldn't work without. So the gamma function is a factorial. And I don't know if you remember what I wrote down as a definition of the gamma function. I think I just copied it from Wikipedia or something like that. But if you let this f be equal t, it'll look just like the gamma function. Well, not just like the gamma function, but there'll be some equivalence to the gamma function. Anyways, that's your HBA, so you think about that. But really, you guys should think about your favorite function. You guys should have a favorite function by the time. Actually, you guys should have a favorite function by the time you get out of this class. Not today, but that should be a learning outcome, huh? Student learning outcome. By the time you finish this class, you should have a... No, that's not a function. What if I asked you this on the final? All right? What's your favorite function? And you get full credit if you actually put a function. If you put an equation, a theorem, a constant, or some other weird thing, then you can't get full credit. All right, that's enough. No, I think it should be your favorite function. All right. So a translation in the S. So Professor Hoffman just walked into some bull, just wasting time. I think it'd be better if we were actually doing math. So let's go back to doing math. Maybe he'll come back. So we just talked about a translation in the S world and how that would look like. And it turns out that there is an equivalent translation in the T world. What would be a translation in the T world? T world is our real world, right? So in the T world, I guess this should be a lowercase t. Alejandro asks, what's this good for? Is there an application? So imagine you have a spring. You know, that usual spring drawing that you have with a mass. So imagine you have a spring, and then you do some stuff to it. You pull it back, you push it down, and then it begins oscillating, right? And then at some point, you start a function. You don't start it right away. At t is equal to 0. Instead, you decide that you start the controlling function at some other point. And so at t is equal to 1, now you start wanting this function to do a certain thing. And so you apply some external force to this function. So that could be seen as, do you remember our differential equation? It has like m y double prime plus some beta y prime plus some k y is equal to an external force that we don't start until a particular point in time. So is equal to, let's call it f of t, where f of t is equal to 0 at some point. I think I called it 1. And then something else. So whatever your external force is, sine, cosine, whatever else you want it to be. So after some point, you apply some external force, but you don't apply it right away. And so that's possible. That could happen, right? That could happen. So we want to allow for that. And this is a translation in the T world, which is different from the translation in the S world. Translation in the S world we only used so that we can find a way to go back to the T world. Now, if our T world originally has some sort of translation where we have some situation where we don't apply the external force until a certain amount of time, then we want to be able to account for this. Now, we could do this as a piecewise function, I suppose, where we have a homogeneous differential equation up to a certain point and then add on that external force and have a non-homogeneous after that. But we can also find a way to put this together, and Laplace Transforms has a nice way of putting this all together. And so we define, this is, I think, called Heaviside Function. I don't know if it's called Heaviside in the book. Oh, yeah, it is called Heaviside. We define a step function to allow for translation. And so we're going to call it script U, capital U. So the script U of t minus a is going to be our translation in the T world. Now, if we have a translation in the T world, we want to know what happens in the S world, right? And so without proof, using that L of f of t business is equal to the integral from 0 to infinity of ... whatever it was. So using that proof, we're going to get this formula for translation. So if we have a translation in the t world, when we take it to the s world, we have to account for that. And the accounting that we do in the s world is going to involve an exponential function in the s world. Okay? So in our s world, we'll introduce this exponential function. Now, we've been dealing with nice polynomials. Now, granted, it's a rational function, polynomial in the numerator and the denominator, which makes it kind of weird to deal with. But now we introduce an exponential. But that's okay, because now when we go back to the t world, we're probably still going to have this exponential, and this exponential says that we're going to have this broken down into a piecewise function, which makes sense, because it's piecewise function in the t world, we go into the s, and then when we go back to the t world, it still should be a piecewise function, because it's nice going at some point, and then you apply your external force, and then now it changes. All right, a couple more formulas to, not really to remember, but if you have piecewise functions that involve more than one function, we can take advantage of the Heaviside function to represent our piecewise function. Now, our piecewise function, our Heaviside function is defined to be 0, and then something happens to it. But if you have a function that's piecewise where something happens and then something else happens, this can be generalized to look like this. So in fact, maybe I should write this down. If f of t is equal to 0 at some point, and then becomes another function after that point, then we can represent this with g being 0. So that's 0, and then this is 0, and then it just becomes the step function, or the Heaviside function, times h of t. Because all these other terms would disappear. And that makes sense, right? It's just taking this Heaviside function and multiplying this whole thing by f. So 0 times f is 0, 1 times f is f, or h. Okay, so let's see how this is going to work. Wait, there's something else. So if we go from the t world to the s world, we should be able to go from the s world back to the t world, and that's our inverse Laplace. This kind of summarizes everything. So Laplace transform and then the inverse Laplace transform. And this time it's being multiplied by your function. All right, let's see if we can at least take a differential equation from the t world to the s world using this, and then we'll hopefully next time be able to come back. Let's see. are my sample problems? I don't have any sample problems. Oh no. I don't have any sample problems. So we're out of time. I want to give you guys a quiz on Tuesday next week, and the quiz will probably be on, I'm trying to decide whether it'll be on a series question or a very simple Laplace transform. I think it'll probably be a series. So something from section 6.2 in class. And you should probably, just in case I throw a Laplace transform, do something from section 7.2. Moises?
Yes, actually I have an announcement